this goes this way, right? And we can just do our good old-fashioned acid-base reaction. These electrons take the H, these stay behind. What does this give? It gives the CH bond plus what? Plus hydroxide. Okay? So that's actually going to go this way. Now, coming this way is the basis for this reaction down here. In the olden days, miners or anybody that wanted a flashlight used to take calcium carbide, which can be obtained sort of naturally. By the way, what's the structure of calcium carbide? It's CaC2. It's actually C2 is, first off, what's the charge of C2? Well, calcium is 2 plus, correct? That means C2 would be 2 minus. Well, this is C2, where you got the dianion. Okay? And the calcium ion just sits with that to balance it out. Here you have the calcium carbide salt. This is just a dianion. But what happens when you treat an anion with water? This anion with water. It protonates. Put an H on each end, and then what do you have? C2H2, and this is what? And what's the name of that molecule? Acetylene. We said it last time, right? Okay. And acetylene is a gas, and it can be burned, and it can, like a torch. You can burn, and you can create a fire, and you can control it. And then you'll make calcium hydroxide. But this used to be a reaction that was done in miners' helmets. Now, this is maybe a handheld, but you have calcium carbide in there, you drip water on it, and you then light it, and it produces a flame. I always wonder, well, how do you control it? How does it generate enough that it's a controlled flame and it doesn't just explode on your head? But you know, 200 years ago, they wore these helmets and they had a little fire up there so they could see. Before batteries came along. They produced acetylene. Yeah? Okay, so that was a miner's helmet. Making acetylene, calcium carbide. It's the reverse of the reaction we showed up there. Okay, that finishes up alkynes. There was a couple of miscellaneous things here. There's a drug with an alkyne. Alkyne sitting up there, lots of rings, nitrogens. Drug for diabetes. Okay. This big old drug, it's not that big, but it's bigger than like aspirin. 1 chiral carbon right here. The rest is not chiral or stereogenic. But because of this right here, we have 2 possible enantiomers. This drug is given as only this enantiomer. Is this R or S? Nitrogen 1, carbon with nitrogen 2, carbon with carbon 3. Counterclockwise, low priority group in the back. Yes, it looks like S to me. Actually, no. 1, 2, 3 is clockwise. Who said S? You threw me off. 1, 2, 3 is clockwise. Let's draw the arrow. Low priority group in the back. R. Well, I'm trying to illustrate here is how to make mistakes. You guys ever make mistakes?
All the time. All the time.
Then you learn from them, right? And then when the test comes around, really the goal is to make as many mistakes as possible before test day.
That's right.
I see a lot of you not making any mistakes though. Yeah, I think it's R. Okay, is it D or L? Well, you have no way of knowing unless you look at the name in the first letter. I think it's L. I think it's L. I think I looked it up. It's actually L, and they decided to use that in the name. Pretty sure. Sometimes, though, you can get fooled because I know a drug out there that the name is like Rolopram or something, and you think, well, it's probably R, and then when you do it, it's S. They're just playing a trick on you. But I think it's actually L. Again, a lot of times the names will include some chemical information. But again, that's just sort of tricky. You can't tell. The rotation of PP light is very hard to determine. Based, it's very random. But it will rotate light one way or the other. And the enantiomer will do it just the opposite, equal and opposite. But this drug is only given as one enantiomer. Okay, there's a variety of other things. But that finishes up the material. We have alkenes, alkynes, and stereochemistry. Of course, lots of alkene reactions. We have nomenclature for both. We have alkene stereochemistry, like E and Z, stereogenic alkenes. Any questions about the material?
So there won't be any thermodynamics?
Yeah, we covered thermodynamics. Everything we covered. If you get anything right now, everything we covered, yeah. Thermodynamics, kinetics, et cetera, et cetera. Huh?
Question about one of these problems in the wood. I thought it was iron, or I thought miso was.
I don't have a workbook. What page?
17.
Page 17 in the workbook. What question? Chlorine is bolded, and the bromine is page 17 in the workbook. Okay, where's Waldo? Do you see a plane of symmetry? This has a plane of symmetry right through here. Half of the bromine going back split by half of the bromine going back. Ring split by ring. Half of the chlorine coming forward split by half of the chlorine coming forward. Slice right through there. There's a plane of symmetry. Since there's a plane of symmetry, is this compound chiral or achiral? Achiral, meaning non-chiral. Now, what was your question?
Why is it not miso?
Why is it not meso? Does this compound have any chiral carbons? That carbon is not chiral. It doesn't have 4 different things attached. It's got a bromine and H, but these are the same. These two paths are the same. So it does not have chiral carbons. The meso compound has chiral carbons, yet it's not chiral as a whole. So this doesn't even have chiral carbons, so you wouldn't call it meso. You would just call it non-chiral. Other questions? Yeah.
So, when determining carbon is chiral, how do you exactly count? A lot of times there'll be carbons, carbon, carbon.
Do you have an example?
Yes, for example here.
One on the
Yeah,
quiz today?
Yeah, because for example, it can go 2 ways. It can look similar, so we can trick into thinking that it's not chiral.
Which carbon? In the ring?
The one in the middle. Yes.
Right here.
Yeah.
Well, we have a problem. I'm not showing any stereochemistry.
Okay.
So you can't determine if it's RS. I'm showing it very generically. I mean, I've got 3 bonds in the plane. I'm not even showing a tetrahedron. It's a very generic, actually incorrect structure. That carbon is tetrahedral. It should be 2 in the plane, 1 forward or back. This bond here should either be forward or back. The question is, does it matter? Well, yes, it would, because if I drew it, like this, that would be one way. What if I drew that dashed? Would that be a different way, or would it be the same thing? It'd be different. I mean, this carbon is chiral. That means it's, okay. I'm just showing it very generically here. And sometimes molecules are shown like this. And we can only determine RS if we're shown one. Now, since I drew it like this, is this RS? Well, let's do it. It's all carbon, so you're going to have to kind of keep going. What's priority? Carbon, carbon, or carbon? Well, how do you do this? You look at what's attached to this carbon. What's attached to this carbon? Well, there's an H there. And then it's double bonded to a carbon, so that's like 2 bonds to a carbon. You write the first one, the highest priority first. Carbon, carbon, H. How about here? Well, there's an H there. It's carbon, carbon, H. How about here? Well, there's 2 H's there. This carbon is attached to carbon HH. Now you look at these, and you see that this is a low priority group. There's going to be of the 3. What else is on this carbon? H. And it's in the back. So the H going back is actually your lowest priority. This is going to be your second lowest, so the H is 4th. This is 3. What wins here? Well, they're still equal. So we still need to go, what's on this? We need to go to the next carbon. This could be a little unique. Next carbon is here. There's an H. That carbon is attached to carbon and an H. Where this carbon is attached to we've got to look at what it's attached to. I mean, we've already looked at that one. It's carbon, carbon, H. We go to the next carbon. We have choices. At this point, it becomes pretty challenging, and we may run out of time. First off, we're looking at one that's very challenging. I'd have to draw them out so I don't get confused. For example, am I talking about, we've already talked about that part. I need to more precisely label these, what we're talking about. Then we're going here. Which one would you go to? You know, we really haven't done an example this complex. This carbon's attached it's got to be this one. This carbon's attached to 2 carbons and an H, where that one's only attached to 1 carbon and 2 H's. So this is carbon, carbon, H. Where here, this was... And what I actually don't know is, when you're here, do you go back this way and say it's carbon, 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 H? That's what I'm actually not sure of. If you just keep going, that's only a CH, C and a H, and thus that is equal right here, this wins. So if that wins, that makes this the high priority. This was second. The carbon with 2 H's was 3. H in the back. And if indeed that's right, that's S, correct? That's a complex example. I don't think any of the ones that I've ever given you are going to be that complex. Usually there's a heteroatom, or you're just not going to have to make decisions like this quite as much. That's a little brain teaser. And I would have to confirm how to deal with this, especially like that. Is this just a C and an H, or do you say it's also bonded to 2 carbons to make this way? I don't think so, because you don't really ever go backwards. So I think that's just a C and an H, where this is like we did, like this. That looks kind of odd. It's like it's only bonded to a C and an H. I think that's what I would probably argue. Other questions? Page 17 at the very bottom. That's an alkene. Like this, 2 methyl. And ethyl here. And this is reacting with what? Hydroboration? Okay, hydroboration. We need to first draw this like this. We just turned it sideways. Yeah? And then we do hydroboration. We're adding water across this. Is the OH going to be on the left or right?
Right.
OH is going to be here. And the new H is going to be here, and they're going to be both up, right? Because it's a syn addition. Syn addition. So there's your product. What's the one shown?
It shows this way, but I just thought, how would I know if the metals were on the same side?
Well, just like this. Why do I have the methyls on both poles? Because it started that way. It started like this. They're cis, and they're still cis. But this has free rotation, so you don't call it cis. But what did we do? We started just by redrawing this. These are on the same side. I just drew them on the same side. Not like that, and this one went this way. But I could also have drawn this the other way. I could have drawn that, I could have actually have drawn these both dashed and put that forward. Hold on. Somehow I ended up with the alpha over here. Did I have it drawn the other way originally? Okay. But you can start either way, and then when you bring in the OH, it's actually going to be over here now. You could have drawn the product like that. But that's just the enantiomer. What is the product? See? Okay, the answer just doesn't say plus enantiomer. The answer should say plus enantiomer. And the enantiomer would be where you draw these both dashed. But knowing that it's plus enantiomer, does that answer the question, or was there another question?
So for the oxymercurization, is that an addition as well?
Do what?
So for the oxymercurization, is that an addition as well?
No, oxymercuration is mercuronium ion, and backside attack gives anti, just like bromination. Other questions? I decided not to. Sorry, thank you. Last questions, guys? This Friday, I'll arrive at 7:30 if you'd like to come ask any questions, 7:30 to 8. Those office hours right here, 7:30 to 8 on Friday. Okay. See some of you in lab tomorrow. Have a good day, guys.